Okay, so if you guys remember, so this is your FET, or let me draw even a simpler version. So I'll just draw this driver. Okay, is there a way I can get rid of this CC? I can achieve the same function without CC. So can anybody think about that? Okay. What if I do this and this switch is controlled by some reset signal which is derived from so what would happen at every edge, whether it's a positive or negative, it will get reset to that voltage to the output. So the DC of that output will be maintained at V out, correct, and that's what you want to regulate. So what you are feeding here now directly is V out signal, correct. So you can still regulate your output without using that capacitor. Which RFB? Then this will short with the output, huh? Then your ripple will be.
Can't we just remove that? Okay.
No, then you remove, then how will you generate the ramp? The V out will superimpose the ramp, huh?
Not this RF, means this the output and this.
Which RF? This RFB you are talking about?
Yeah.
That's what I am saying. Then this ramp, this will, V out will superimpose the ramp and you will not get a ramp at all. You will only get the output ripple, that's it. You want to make sure the AC component here is your ripple and DC component is V out. So how do you add the AC and DC? If you short your AC and DC, then who will dominate? Then DC will dominate, obviously. So your V out will dominate and it will be looking like same as the output ripple. Then you will again get the same instability which you are basically effectively making it voltage mode control. If you directly short this, then this is useless actually, or this RFCF filter is useless in that case.
No, not shorting it. If we remove this, it's like open circuit here, RFB, if we remove that, the DC voltage of the V out is coming at the.
Oh, in that sense you are saying? Yeah, it's effectively same thing, huh? Because this signal is dominated by that, okay. It's same thing. There is no difference whether you put a RFB or not. But if you don't use that, if you have a CC, then you require that RFB. Without RFB, otherwise your output will be dominant. But I mean, in a sense, we always want to so let me see. No, I think you will require RFB here, otherwise it will be a problem. Sorry. It will work, but the problem will be your transient response may not be as good as, because now you have two paths. If let us say your transient V out, you apply a transient during when it is charging or discharging this voltage, okay. That time there is no feedback from V out, because you are shorting the V out for a very short duration only at the edges. In between you are not sampling the V out. So, the only path to correct the transient is through this cap, feed forward cap. Okay. So, it all depends how much component this is passed from output to this VRAMP node, if I call it, let us say VRAMP, through this CF cap. But if you have the other path, then you may get a better transient response. I mean, that will work, but maybe you may get some degradation in the transient response. So, advantage here is you have a direct path. So, anytime V out changes, it will get reflected here. But in the other case, you have to wait until the next cycle comes. Otherwise, you have to only rely on this capacitor CF. It's a feed forward. Okay. So, now, so you guys remember we tried to initially do it with the GMC integrator, the RAM generator. Now, if I do the same thing, I remove this, or just let me copy it. So, here okay. So, what was the problem with this? This was grounded, sorry, in the integrator this was grounded. So, what was the problem with this? It will saturate. So, now if I reset this, to V out, then it will not saturate. Every cycle you are resetting to V out. So, the DC will remain at V out. So, it will not saturate. So, now with this reset concept, it will work with GMC integrator also. So, you do not require resistor. Okay. And now remember the fixed frequency static where you had FLL and everything. Now you can control the GM instead of controlling the R, and GM can be controlled by simply using. So, there we were using RDAC, now you can use current DAC in the GM cells and you can control the GM table. So, without resistor you can do. And since you can, I mean, achieving a smaller GM is maybe easier compared to your RF. So, if you let us say RF required is order of mega ohms, then you may save lot of area by doing with GMC rather than going with this RC filter. Okay. So, constant on time. So, we know V out is nothing but D times V in or VDD. So, now if I keep this on time constant T on and T off is Very. D is what? T on over TSW. So T on over T on plus T off. So I am changing only this. I can still control the duty cycle, but the impact is what? TSW okay. So how do we do it? So again you just require same hysteretic loop everything. So I am showing a voltage mode here conceptually, but all the issues we already talked about, that you require a large ESR, everything is valid here as well. But just to show you guys the concept, I am showing simple voltage mode. T on generator. Okay. So we want to make the T on constant. I mean T on generator, there will be one, let us see. We need a flip flop. Set, reset. So let me build logic. So let's say my ripple is like this, and when we look at the peak current. Okay. So what happens? It's more like a valley current mode. So whenever your output goes below some Vref, let's say this is your Vref, what you do? You immediately set this flip flop, and your on time you are forcing is a constant on time. Correct? That will be fixed, and it will get set so let's say this is your this is some Vref. So this is your T on, which is your forcing. Okay, after that you reset, after T on, and this portion is T off, will be controlled by the feedback loop. Correct. So whenever this guy goes below your valley or Vref whatever, then you set it again. Okay. So when this guy is below, this will flip flop will trigger, and then you again trigger your next T on pulse, which is a one shot pulse, and that on time is in your control. So you just fix that, you are not changing that, but the discharge is, I mean discharge is depending on so many things, your load current and everything, but your this comparator will not allow this to discharge below Vref. So this on time will always be forced in such a way that your output is regulated. Okay. So how do you build the logic for this? So the reset will come here. So the reset will be, so if you remember we are resetting, so we are forcing here and then, so I think you need to reset at so you need to set at negative of this. So if I set it at negative edge of this, this is your edge detector. So we are setting here, when this goes below, this will give 1, okay, and you set, and then now you want to pass, you want to reset at what? So where will this reset come? This reset will come from this T on generator. So I will put another edge detector here. Okay. So basically you start counting when this goes, this comparator goes high, you start counting and you wait until your T on is passed and then reset your duty cycle. Now this comparator is relying only on the output. So where will your output be regulated? At what value? Yeah, so whatever the ripple is, if this ripple is, let's say delta V out, then V out equal to Vref plus delta V out by 2 roughly. Okay, so this is not regulated at Vref at all. So you will always get this much error in this. So how do we fix this error? So the same way you can do a constant off time also. In the constant off time you will be looking at the peak. So that will be more like a peak current mode. This is like a valley current mode. So your average will be minus delta V out by 2. So how do we fix this? Do you guys remember it?
Before we set the...
No, but that your slope is uncontrolled. I mean, slope is not fixed. Huh? So if you rely on the time, that may change. Your ripple is also variable. If ripple is fixed, then you can fix it. That's not a problem. But ripple is variable. Huh? I mean, in the hysteretic mode, you are controlling both valley and peak. So you are basically regulating the ripple. Here I am not regulating the ripple. You can adjust Vref. Huh? We talked about this earlier. Put an integrator in the feedback and adjust the Vref. That's it. So which means I need to, instead of Vref, I need to have a Vref minus delta V out by 2. So if I have an integrator in the loop, if this is Vref and this is V out, then this becomes Vref new and you control this at Vref new, that's it. So this integrator will automatically force your Vref new to a value for which V out equal to Vref. So this Vref new will be nothing but Vref minus delta V out by 2. Okay. So, it will cancel out that error. If you are doing a constant off time, then this will become off time generator. So, now frequency is variable here. Is there a way I can fix this frequency? Or so if I want to fix the frequency, what do I need to do here? I need to adjust both T on and T off. And T off I know automatically adjusted by the loop. I am forcing T on here. So, whatever T on I am forcing, if I change that based on V in and V out, then I can regulate the frequency. So, now you can do the same thing what you did there in the previous case. I was controlling R there with the FLL. Now, you control T on with the FLL, that is it. So, your on generator, whether you are doing a digital or analog, so your this T on generator could be either digitally means you count the number of pulses of a high frequency clock. Okay. Another way, T on generator, so if you are doing it digital, so all you require just a counter. So, this is your clock, this is high frequency. So, your count, so if this is your reset, this is your count comparator and you reset this counter. This is your reference code. Okay. So, let us say this is 100x of PWM, which means let us say 1 megahertz is here, then this will be or FSW, I would say 100 megahertz, correct. So, if I want to keep this T on 100 nanosecond, I fixed 100 nanosecond, how many counts I require? 100 megahertz by? So, how much is that? How many counts? 1000? What is the period of this? 100 megahertz? 10 nano? 100 nano means how many period you require? 10 cycles, huh? So, only 10 counts you require. So, if you count 10 clock cycles of this 100 megahertz, you will get a, and after that you reset it. So, your counter output will be giving you a pulse of 100 nanosecond, correct. So, that is how you generate. So, that is a digital way. Now, equal to 10 for 100 nanosecond T on. Now, I want to vary this, which means I have to change the reference code. Now, from FLL you generate this reference code and that will automatically keep on changing when your frequency varies, that is it. So, it will automatically increase or decrease. So, control from FLL for fixed frequency. Now, if I want to do analog way, how can I do it? The same thing using how can I generate this fix on time? So, I have a current, let us say I will call it I on, this is C on. Okay. So if I have a comparator, some VREF, minus plus, okay. And this will be your reset. And this will be reset coming from the same reset, your this guy. When the time at which you want to generate the on time, which is the comparator output, you will reset the switch and it will start from 0. So when it start from 0, it will be high, and when it crosses your VREF, it will go low. So what is your T on here? I equal to C dV by dt. dt is your T on, dV is VREF, and that is C on, I on. So how much is that? T on equal to C on over I on into VREF. So you have two components which you can control, two parameters, one either this or this. So for fixed frequency, FLL can be used to control ion or VREF. Okay, so you require current DAC there or voltage DAC in case of VREF. So this is nothing but a hysteretic control, but you are not limiting that inside a window. You are only limiting the peak or valley, and the other side will be controlled by your feedback loop. Okay, then how to generate the ripple and all those, you already know, the same concept will apply, because it will become unstable. If you don't have a large ESR here, it will again, you will have the same problem, the phase lag and everything. So your ripple and everything will be generated in the same way. You use this RC component, everything, but you are now only controlling the peak or valley, that's it, or the limiting your output peak or valley, not the window like we are doing in the hysteretic comparator. So that's why in terms of stability, this is much better, the hysteretic, compared to your constant on or constant off, because here we are limiting both. But what about the transient response? Which will be better in terms of transient? Which will be better? Hysteretic, I mean that hysteretic or constant on or off time in terms of transient? Just think about it, it's simple. Why?
Because their on time can be as much as you.
No, but same thing here also. Not as much as, how do you say as much? You are still limiting within that window.
No, but till the time the current of inductor is rising, we can be on for that.
No, but that you cannot guarantee there, because you are limiting within that window. So if your inductor current tries to rise, then your comparator output will also try to change, input try to change, and then it will just reset the duty cycle again. It will not allow inductor to rise all the way where it wants to.
It is higher on you. Dion will be.
No, I mean, in a way you are limiting the inductor current only by limiting it within that window. If you limit it within that window, until unless you make your hysteretic window very small, correct? If you make your hysteretic window very small, then any small change in the output will be sensed, and it will basically, your comparator will make the output all the way high or low. But usually you do not make that hysteretic window very low, because you want to make sure that your ramp amplitude should be much higher compared to your output voltage ripple, correct? Otherwise, you may again see the same problem, instability. We talked about the two components are there, in phase and out of phase. So, you want your in phase component to dominate, not the 90-degree out of phase, which is your output ripple. So, I cannot make my hysteretic window 10 millivolt, otherwise I will again have the same problem. So, usually you make this hysteretic window 50 millivolt or higher. So, now think about, I am not limiting the, so let us say I am using off time, constant off time. So, I am limiting the peak, and if using on time I am limiting the value only. So, in this constant on time, my peak is free to go anywhere. Huh? So, let us say moment you get the transient, your output dips, your inductor will keep charging, correct. So, your loop can allow there to turn on the duty cycle for longer time, because I am not limiting the upper side. Same thing when you release the load, and in other case you may get a better transient response. Okay. So, but the moment I try to limit that inductor current, obviously it will impact my transient response. I mean, you can simulate and see the difference between voltage mode and current mode. In the current mode, you will see your duty cycle won't be on for a very long time, because your ripple, this hysteretic comparator will limit that. So, it may take few cycles to go that there.